I'm going to start off with first a brief demo of the VR system, just to kind of show you, first to give you a taste of what you'll be able to see if you try it for yourselves. Obviously, you're not going to get the depth perception that I do, but hopefully it'll give you an indication. And then I will switch back over to Vision 4D and show you some of the way that we approach big data. Tamara showed you some of this already, but I'm going to go into a little bit more detail. So for the VR, we're actually using fairly standard hardware. So we're using an Oculus Rift headset and a gaming card, specifically a NVIDIA GTX 1080. It's a good gaming card, but the PC itself isn't actually amazing. It's, I mean, it's Core i7, right? So it's not like dirt cheap PC, but it's, yeah. Okay, and so when you put the headset on, you immediately get to see the data. So at the moment, my data set is, well, let's go. Okay, here. And it's a little bit easy to see if I actually show you the controllers. So you should be able to see on the screen essentially what I see. You see the controllers, you see the data, and if I put my controllers inside the data, you can see that it's actually depth dependent. And that's one of the key advantages of working in VR, is that you're not limited by the windowing effect of working on a screen. So when you click on an object on a screen, your software will be estimating the depth that you're clicking on. And you know, we have those same systems in our software, and they're fairly good, but they're quite limited. So there's several things you can do. So well, for a start, you can just kind of walk around and take a look from different places. You can dip your head in and see different structures. And one of the great things that we do with our software is that we do what's called volumetric rendering. So the key advantage of using volumetric rendering is that we can go from the acquisition to the visualization like this in a matter of seconds or maybe minutes. In this specific case, it took a little bit longer because I actually did a little bit of data processing. So I did some background correction to make it a little bit easy to see the structures. So when you look up close, you can see individual projections. Come back here. Okay. Right. But you can also go inside now because it's nice and clear, and you can follow processes throughout and see where they originate and where they end. You can see cross connections going all around. If you want to mark a point of interest because you'd like to share this with some of your colleagues, you can do so by just pointing in a space, and because it's depth dependent, if I put it on that cell there, for example, you can see it is actually on that cell, not just kind of somewhere in the middle. Because the problem when you click on the screen is it'll find the first most opaque pixel that it finds, and sometimes it's there and sometimes it's like way in the distance, and it's just a really tedious process. There's actually a few marks that Mike did earlier, so we've got them here. And we can also record points of interest. So if you want, not just point of interest, but point of view. So if you want to be able to export this as a high resolution snapshot, like Tamara showed in her presentation, that's entirely possible as well. It's not something that you want to do live because you want to be able to have this dynamic interaction, but it's certainly possible. Another thing that Tamara mentioned is the ability to measure things. So we can switch to the measuring tool, and we can just measure simple things like the distance from one point to another with instant feedback about the distances we're measuring. But we can also measure much more complex things, so like long distances. And this is where, again, being able to follow along is really important, because we can actually see exactly where our processes go. And well, I should have picked a better one, because this one just ends in the middle of nowhere apparently. No, it's over here. So another key advantage, if we find that we're actually not following quite right, we can just reposition it like this and then follow it along. Okay. With the other advantage of the the volumetric rendering is you can also see inside of the data. So if you slice through, you can actually see inside the pixel intensities inside of the object. The traditional methods of VR rendering use what's called surface rendering, where you create a mesh around the object. And it has its advantages in that it's very cheap computationally and it's very fast, and you can render very large volumes like this. But the downside is that you can't just kind of look behind the surface. Tamara mentioned the ability of creating the ability to create regions of interest. So if we're interested in maybe measuring or counting cells in those very specific regions, we can do this as well. So we'll start off by creating a little blob here, and then I can sculpt this blob into the dimensions I need. And so we just trace there in 3-dimension. Okay. Right. So if I'm only really interested in this region of the brain, or maybe I want to differentiate between this region and another, I can draw this region very quickly. And I did it kind of quick and dirty here, but already, this is about 10 times faster than you could ever hope to manage on a flat screen for manual region selection. And then you can take those regions and export them to Vision 4D. So I'm going to switch back to Vision 4D now, and I'm going to show you some of the way that we deal with this data for the image analysis. I'm not going to take the same data sets. I've got another one which is a bit more funky. I got it about an hour ago, and I've just done some a little playing around with it. And my screen is off. That looks good. Except I'm gonna go there, because then I can see my screen and you can see what I'm doing over here. Right. So this is Vision 4D. The interface is fairly familiar. We've got windows, menus at the top, shortcut toolbar, so you can get access to common functions, and some tools over on the right, just so we can manipulate the data. And opening the data is pretty quick and easy. You just drag and drop it. So as you saw, that data set was 200 gig, and that's it, and it's open, ready for me to work with in Vision 4D. And what Vision 4D does is it loads the data that we need as and when we need it. Okay, so we've got a relatively good projector here. But even that projector, if I look at the display settings, right, it is 19820 by 1080, right? So we have 2 million pixels of screen real estate, but we have a data set which is 6,000 by 7,000 by 2,000 by 1,600. So there's no way we can show you all of the pixels in the data set on the screen. So why hold them in memory, right? So what Vision 4D does is it loads the pixels that we need as and when we need them, and this is what gives us this really high dynamic advantage. And then you can just very quickly select a region of interest, and I just drag and drop, and instantly I get that region of the image. I don't have to wait, I just go and see it. So this data set has dual staining. In green we see the vessels, and in red we have some immune cells. What Mike is interested in this specific case is actually to look at the effects. So here in the top right we have this, top left we have this lesion, and we're interested in comparing the number of immune cells that might be in the corresponding region on the right-hand side. So with a data set this big, 200 gig, if we want to process the entire data set, it's going to take time, right? Your computer is going to have to read, process, and write that much information. And I say read and write, this is quite important because we load the data that we need as when we need it. That means we only use as much RAM as you have available. And so if your data set is larger than the RAM, we have to have somewhere to store that data. And what we do is, instead of forcing you to buy lots and lots of RAM, is we say, well, why not just use really cheap hard drives to do it? Because we have a very fast data access that allows us to do this seamlessly. So the one thing that we require from you to be able to do image analysis on a terabyte data set is that you have more than a terabyte worth of free space on your hard disk to hold the results, right? Now, saying that, I had to stop and buy a removable hard drive for my colleague to exchange some data. He's going to come and fetch it from me on Thursday. Stopped at the airport, and I bought 2 terabytes hard drive for about £70 or 80 euros, right? So storage is dirt cheap, really, when you consider that, well, most computers these days won't even allow you to put in a terabyte of memory. At best, you'll have 512 gig. That really means that you'll be looking at 256 gig of data is the biggest data set you'll be able to manage. And even then, right? Okay, so we have these cells and we're looking to count them essentially. So there's a few things we could do to improve this data set. That's all right, that's fine. So in this case, what's going on? Yeah. I'm going to start off by just working on just this small region of the image, just so I can show you dynamically what happens. And then, obviously, if we want to run on the whole data set, then we just need to give it some more time. So the way you do this in Fiji or any other software essentially would be to say, well, crop the data set. Well, we don't really need to crop the data set. We can just say work with this region of the image. So if I say work with the current view, it's going to work with just this region of the image. Now we're looking at 3D objects, so looking at this 2D view is not necessarily so useful. So I can actually set custom volumes. So I can say I want to work from plane 500 to 600, right? And that's it. I'm not duplicating any data. I'm not creating lots of artificial data sets. I've just said this is a part of the data set that I want to work with now. And then we'll drag operations into this pipeline. So here we have a lot of autofluorescence. So we could start by doing a background correction. As Tamara mentioned, we really focus on making the software usable and intuitive. And so one of the things we do is we offer you the ability to do live preview on the screen of what those filter operations will do. So you can see instantaneously the effect of doing a background correction, and you can see whether we're wasting our time or not, and you can see the speed that we have for this process, right? So I'm quite happy that this background correction setting is going to reveal the structures I'm looking for. So then I can run this operation, and we can see in the top left, it's going to take a couple of minutes because we do have 100 100 planes to process through, and it's taking a bit longer than I expected.
Do you have a function to cancel it?
I can cancel it at any time, but there we go. It's just sometimes it takes a couple of seconds to get started, that's all. Right? But right there at the top of the pipeline, I've got several tools that allow me to play through to the next operation in the pipeline, roll back an operation. So if I want to change the parameters, if I'm not happy with that, I can do this. And if I want to cancel the pipeline because I can see it's obviously painfully slow, then I can just do that here.
That's good. In many softwares, it's canceling this problem. It crashes if it gets stuck for a long process.
Yeah.
It cannot do anything.
Yeah. So this is one of the key focus in our engineering department, that the applications should not crash, right? It will take time because there is a lot of data to process, but we make sure that as much as possible it doesn't crash. That's actually one of the main pieces of feedback that we've had. We did a demonstration at the Pasteur Institute last month. They had a trial version of the software with them for a week, well, actually almost a month. And the one piece of feedback that they gave us that was a kind of like overarching comment was, it's just stable. You can have 5, 6, 7 viewers open simultaneously working on different images and it doesn't crash. Okay, so anyway, so I've got this these cells now very clearly visible, so we can go on to segmentation. So obviously we have the typical segmentation method. So if you want to do an intensity threshold, you can do this. And again, with the ability to preview on the screen what you're going to get. So I can click on the image, right, and say, right, I want to include all of these pixels in my intensity threshold. And we can choose the color. I'm going to call this operation vessels. Right. And then we can run this operation and it will do the analysis on that part of the image. So that's it. It's found all the blood vessels in those 100 planes. Got to stay within the range of, there we go. Okay, but obviously just the blood vessels is quite nice, but we're actually really interested in the immune cells, so we can do a second segmentation. And in this case, what I'm going to do is use a segmentation called the Blood Finder. This is an operation which is based on a 3D watershed filter, essentially. And it's particularly well suited to finding cell bodies, cell nuclei, roughly globular structures. Again, we have the ability to preview on the screen exactly what it's going to look like. Yeah, maybe yeah, that should be. That looks pretty good, actually. Okay, and then run this operation, and we're going to find the nuclei. So this operation takes a little bit more time than the vessels, as you can see. But there we go. We found those nuclei. Actually, what I might do is redo that one and change the color so we can see them in a different color. Make them blue, for example. Okay. It didn't take too long, so I don't feel too bad running the operation again. Okay. And those are 3D objects, right? So if I switch to the 4D view now, we'll be able to see those objects in situ as actual 3D objects. Go on. So there's the region where I analyzed all these objects. At the moment, I'm just showing centroids, which, you know, maybe isn't so much fun. But if I switch to looking at right, so these are all the cells I've identified. And clearly the Z spacing is somewhat larger than the XY spacing, so that's quite visible. And then if we're interested in measuring the distance between certain types of object, then we can use the segment colocalization. So for the segment colocalization, we're going to use the vessels as a reference and find all of the cells that we identified using the blob finder that are within a distance of no more than, let's say, 5 microns. So then I can run this operation. It's going to take a little bit of time because we have some very complex structures in the vessels. But here now we have all of those those cells that are within 5 microns of, did I say 5 microns? Doesn't matter. Come on. It says not responding, but it's just waiting. Right. Okay, so if I look at the segment colocalization now, we can see that we have 400 cells that are actually within, as I said, 5 microns of the blood vessels. If I look overall, we had, in the annotations we selected, about 3,500, right? So we could say that 10% of the cells roughly are within 5 microns of the blood vessels, right? And that's fairly informative. Now, all of this I've shown you currently with the current release version of Vision 4D. We're actually working right now on the next version, which is making some major upgrades to a lot of aspects of this workflow, including the ability to have very easy color coding of the objects, have the measurement distance available in the data table. This data table, obviously, we can export. So if you want to output it to an Excel spreadsheet, you can do this. But when you have billions of objects or millions of objects, and maybe that's not always feasible. But the other thing you can do, obviously, is store the results directly within the SIS document. So when you save your data, you can open this data on another computer. And that can be quite useful because you may have a really capable computer in the basement of the facility with a Xeon processor and lots of RAM, which is really good for the data processing, but that computer might not have a great graphics card for the data rendering, right? And so you could do the analysis on your downstairs computer and then transfer the data set with the results all the way to your laptop, which has a really good gaming card or whatever, and then do that rendering work as well. So the reason I did this pipeline on this small section is partially just to be able to test that the pipeline is working, partially for speed. But now I can just roll back this pipeline all the way to the selection. And I can change the selection to say, I want to now run this on the entire data set, right? And then I can leave it running overnight, over a weekend, over a short holiday break, depending on the size of the data set and the complexity of the analysis pipeline. So that's how we approach image analysis. We have only implemented in our software methods of image analysis and strategies that will work regardless of the size of the data set, right? So we've made a strategic decision not to include filters that would be RAM limited. So things like a distance map measurement, for example, we will not implement because you must have the entire data set. Now, in any case, you don't want to use a distance map because it's a rubbish filter because it only works with isotropic pixels, right? But it's just we instead decided to implement a segment colocalization, which is based on the segmentation of the object and vector-based analysis, which works regardless of the data. So that's it as a brief overview from me of the type of analysis that we can do with Envision 4D and the type of visualization and measurement that you can do in InViewer. As Tamara said, we are going to be here all week. If you'd like to book a slot to come and see us, you're more than welcome. I think, do you have a sign-in sheet or something, Tamara? Come and see us at the end, and I'm sure we can work something out. We'll be in the kitchen area, and if you have some of your own data sets and you want to have a look at it, you can do that. But otherwise, as Tamara said, you can also request a trial or even an on-site demo if you think your institute might be interested in getting some of this. So thank you very much.